wanna talk a little bit about the memory management?
Oh, sure.
Couple of corrections for the first video that we did. Number one is I said a stack was first in, first out, but that's actually wrong. It's first in, last out. Yeah, if you think through that makes sense. Like a stack, you put in the 1, you put in the 2, you put in the 3. If you pop, then you get rid of the 3. If you pop, you pop again, you get rid of the 2. So the 1, which was the first in, it actually comes out last. So that's a correction. Another correction, I was reading some more about garbage collection last week, and originally I said Python was a normal GC, but it turns out Python also uses reference counting. So it's not true that Python uses the normal GC. It uses reference counting as well, which I did not know that. And then also in terms of terminology, I got that wrong also. so turns out if you look at the Wikipedia page for for garbage collection, turns out that the automatic reference counting is also considered a type of garbage collection. So I was separating them, but maybe ARC should be under the umbrella of GC.
Are we gonna dive into the concept of the ARC and the GC?
Yeah.
At some point.
So I was saying ARC is distinct from GC, but in fact ARC is one type of GC, and the other type of GC is, they call it in this article, they call it tracing. So yeah, we definitely want to cover what these concepts mean. Let's first talk about ARC, which again stands for automatic reference counting. And let's start with an example. If you have a function and inside of it you make an array, and then maybe you call another function within it, passing to it the array. So this array, the numbers, the A and B, which we assume are like numbers, they're not gonna be stored in the heap, because the numbers just get stored in the frame always. When you make an array, we're gonna allocate heap memory to store the value of the array. The question is, how do we know, like if we have a heap and it's storing the values of our array. So if I'm gonna call f with 1 and 2 at some point, so the frame is gonna be like that. So at the bottom of the stack, we're gonna put A is 1 and B is 2, and the array is a pointer to this guy, which is going to have 1 and 2. And then now we're going to call G, and G's array is going to be pointing to the same array in the heap. So when G is done, when G finishes, this pointer will go away. When F is done, then this pointer will go away. The question is, we would like a system that knows when no more pointers are referencing this array, then we know this can go away. We don't need that.
How does the system know how many pointers are there? Where are the pointers stored? Are they stored in the frame, or where are they? The registry of points.
That's a good question. So in the reference counting system, what you do is this: you keep a reference count for each object that's in the heap. And the way I'll do it is I'll just put a little number here in parentheses. So at this point, we have a reference count of 2 because there are 2 pointers pointing to it. There are 2 references to this array. Therefore, the reference count is 2 at the moment. And if G finishes, then this pointer goes away. Therefore, this reference count should go down to 1. And then if F finishes, then this array pointer goes away. And then the reference count should go to 0. And when your reference count is at 0, you know that you can destroy the array itself because nobody else is referencing it anymore. So the way it basically works is every time you assign a heap object to a variable, you increase its reference count. So for example, you have another variable, y array equals array. If you do that, you just increase its reference count again because now there's 2 references to the same array. And when you pass the array to another function call, that increases the reference count because inside of the function g, well, this pointer just got copied to this parameter here. So this parameter is pointing to, so that increased the reference count again. Yeah, so that's more or less how that works.
We talk about automatic reference counting, right? Is what we just talked about, like automatic reference counting?
Oh yeah, is this automatic? Well, if your language does this for you automatically, then it is automatic reference counting. But if your language does not do it for you automatically and requires you to notify it yourself by calling some function, then it's not automatic reference.
Gotcha.
So in an older version of Objective-C, they would actually require you to do this manually. If you had an object, if you want to increase its reference count, you have to call the retain method. So you would call retain. And that increases its reference count. And then later on, if you want to decrease the reference count, you call release.
Interesting.
This is very interesting. So I'll just read this paragraph. So while Objective-C traditionally had no garbage collection, and when they say it had no garbage collection, at that point, basically it had this manual reference counting mechanism where you have to call the methods yourself. If you say retain, basically they're saying, well, within the scope of what I'm using it for, I need it around, so I'm gonna retain it, which increases its reference count. And then when I don't need it anymore, whatever the definition of my scope that I choose it to be, and when I don't need it anymore, I'll release it, right? So I'll call that manual reference counting. But then in 2007, Apple introduced garbage collection for Objective-C 2.0 using an in-house developed runtime collector. However, with the 2012 release of OS X 10.9, garbage collection was deprecated. Like that one that they made in 2007 was deprecated in favor of LLVM's automatic reference counter, ARC, that was introduced with OS X 10.7. Since Apple even forbids using that first garbage collector that they made, garbage collection has never been introduced for iOS. Oh, what we talked about is only for the OS X. But for iOS, garbage collection has never been introduced due to problems in application responsivity and performance. Instead, iOS uses ARC only.
So what's the difference between garbage collection and ARC here? Because I thought ARC is a mean of doing garbage collection.
I guess they are distinguishing kind of between garbage collector and ARC. We'll talk about what a tracing garbage collector does later. But essentially, a garbage collector that they introduced in 2007, that one had a more severe performance impact than ARC. ARC is more lightweight, and the full-fledged garbage collector just took up more resources. So Apple has always been very conscious about performance in everything that they do, which I think that's the reason why they prefer to not have a full-fledged garbage collector. Apple might be a special case in that because most of the developers in the world use a language that uses a full-fledged garbage collector, including JavaScript and Java. Those languages use a full-fledged garbage collector, which does have a performance penalty, which we'll talk about. ARC has a lower performance penalty in general. At least that's how it is perceived. Although technology is always advancing and people are trying to do better with either approach all the time. If we try to keep track of the different places where we would need to increase or decrease the reference count number, those places would be so you would need to increment a reference count if you assign a heap object. I'm just gonna say object, but I mean a heap object to a variable. If you pass it to a function as an argument, if you assign it to a field of another object. If you have one object in the heap that has a field that's pointing to another object in the heap, then the assignment to this field should also increment this number here, because that's also a reference to this object. Where to decrement the reference count. So if you assign an object to a variable, you could potentially need to decrement the reference count of the object that the variable used to point to.
Gotcha.
So if you have like an array variable and it's pointing to this array in the heap, and then you're saying assign another array to this array variable. So you're gonna remove this link, you're gonna add a link to here. Well, this one is gonna +1, but this one you wanna -1, right? If you assign to a field of an object, it's the same thing. You need to decrement it.
What about after you pass it to a function and that function returns? Do you decrease the?
Yeah, exactly. That's a case where if you have a function that's receiving an array, or there's another array, this is pointing to an array, and this guy is gonna point to another array. Basically, when you reach the end of this function, then both of these should -1. Basically, you're removing all the resources that are claimed by this function. This function is done, so it doesn't need those resources anymore. So you wanna -1 on everything that's a reference of some variable or some parameter in this function.
So what if you have closure? And it's gonna make things more complicated.
Yes, exactly. When you have closures, it makes things more complicated. We probably should talk about closure, but before talking about closure, I'll leave this list as is because these are the big cases. Now I'm going to talk about special cases. So if you return a heap object, so for example, you have a function So your f is gonna make a heap object, put 1 and 2 inside it, and then it's gonna increment the reference count because it assigned it to a variable a, and then it's gonna return it. But since we're done with this function, it's gonna minus 1. Right?
Okay.
So, well, okay, that's a problem because maybe in the h function we called function just to instantiate this array. If you decrement it to 0, you're gonna x out of this, and then this has nothing.
Well, but when you are so this case, I guess normal case, when you assign to an array to my variable in the h, it's gonna add 1, like increase by 1. But in this case, because it's not like literally assigned to an array, so it's kind of special because the array returns.
Because the array returns, you don't want to destroy it before the caller has a handle on it. If this is not destroyed though, here you would do a minus 1. If you deferred it, then that might work because the outside would do a plus 1 on it right after it receives it. And then if you defer this minus 1, that minus 1 would happen after this plus 1. So it will not end up going to 0. So that's one potential way you could deal with it. There may be other ways to do it. I don't actually know how Objective-C deals with this case, but that's a case you have to worry about if you are like implementing a programming language that does this. But if you are just gonna tell the programmer, hey, you do it yourself, then it's kind of up to them to come up with their convention of when to do that. Let's see how it would work with closures. Does this illustrate the point enough? Let's say the array initially has reference count of 1. Let's just say 1 and 2 are in the array. So it goes here, we're gonna increase the count to 2 because of this function parameter here that references it also. Oh wait, this is not a good illustration, so I'm gonna cross this out. I'm gonna return the function g.
Right.
So that f will terminate before g terminate. I have a special g star is equal to f of 1, 2. And then we're gonna call g star with the index number of 1. And then it's gonna return the number 2 to us. So what should happen here? This actually doesn't have a reference count because I didn't assign it to any variable. When it goes in here, it has a reference count of 1. The instantiation of this g function here, we have to look at this inner function as an object that's retaining this array. So because this g is referencing this array from the closure scope, we're gonna have to increase the count here. This doesn't matter, as g needs to be reference counted as well, I think. So g is gonna have a count of 1. And g is pointing to this array that's represented by increasing the count here when we initialize g. G has reference count 1 because we at this step we've assigned this function to g, and this array gets incremented because this function references the array. And then when we return g, we get into this problem of we're trying to return the thing, so maybe we defer the minus 1 here just a little bit so the outside has a chance to catch it. So in any case, this is like a minus 1 plus 1 situation. Right. So that when we're here, the reference count is still 1. And then, but the reference count, here decreases for array because f finished. The reference count for the array decreases to 1, but it's still not 0, so it keeps alive. And now if you call g, g can access this array.
Gotcha. So basically, the key is you just see the function that gets returned as an object that has a field of an array.
Yeah,
basically.
you don't have to think about it as the function itself, but it's the closure of the function. So maybe we call this the G closure, and the G closure is basically the set of variables that G has to keep remembering the closed variables. The closed variables. If you read the Wikipedia article about closures, it'll say the closed variable is a variable from the outer scope that the inner scope is referencing.
Right.
So our closed variable is array 1, but there could be more. So for each one of those closed variables, we need to stick it into this little container here. And we're gonna and that's allocated on the heap as well. So yeah, so I believe LLVM's automatic reference counter thing, I believe that's more or less what that system does, is automatically generate these instructions to increment and decrement the counter, etc. Like performance-wise, this is not great actually, because if you just think about what a program does, that it could potentially generate a lot of these instructions just to add 1 and -1. There could be just many of those inserted into your program, that can impact performance. And so there's some optimizations that people have worked on. There are cases where the adding 1 or subtracting 1 are not really necessary if you analyze the source code, and there are optimizations to sort of remove the ones that aren't totally necessary. And I haven't looked deeply into how that stuff worked, but there are like computer science papers on that kind of stuff. A while ago, I created a programming language called Chameleon. I actually allowed you to switch the memory manager between normal GC or ARC. Like this is a struct that has 2 fields, 2 integer fields, and when you make a new struct, you actually, instead of saying new in this language, you say alloc, because I wanted to make it very explicit that you're allocating. So when you alloc, you're allocating this struct onto the heap. Like there's a new object on the heap with A and B in it. And you have an option of not using a memory manager, and if that's what you did, then there's no freeing of anything. If you want to free anything, you actually have to call the free operator. You would have to say free it manually. But if you use a memory manager, then it'll be scope based. It'll say at the end of the scope, it'll actually try to free this guy. At this stage of my implementation, I asked the programmer to write a release function for every structure, and then it'll automatically, based on the name, it'll automatically call this function.
Okay. So the point is,
this is only for, in this case you don't need it, but this is only for if one of the fields points to yet another structure that's allocated on the heap, then you would want to like release that one. Like if this guy has like a person, and then you would like you want to release person.
So the point of release number pair is
if there's another pointer to another heap object, this tells the compiler how to release that guy as well.
Really for the okay.
Yeah, but
I guess.
Yeah, but this is a small, like, maybe I don't want to dwell on that. It's just like maybe I could have done it automatically too, but at the moment I haven't.
So I guess the point of manual like garbage collection system. So maybe in the real case that the programmer will not increase or decrease in each step, but they want to say, hey, when the program ends, when this particular module finish, I'm gonna release all of them together so that they don't have to use their memory on the minus one plus one.
Or
Will
use
that be
instructions. Yeah, yeah. What you're saying is an important point, but which is you're saying that a programmer can potentially implement this more efficiently because they have more knowledge about how the program works, and therefore, if you try to do everything automatically, produce some inefficiencies probably, and
right?
and that's very true. That's very true. One example of that is in one of Jonathan Blow's videos. Jonathan Blow, the indie game producer who also made a programming language for making games, one of the innovations that he made in his programming language is something called the temporary storage buffer. He actually utilizes how a video game works as a trick to make his memory management faster. The video game has this while true. Almost all video games are like this, like handle events and then update game state and then render game, right? Like basically he made up a section of the heap, temporary heap, let's call it. Within the code of any of these stages, you can allocate memory from the temp heap. If you do that, it'll just like first come first serve. Like the first one will get this chunk, the second one will get this chunk, third one get this chunk, and so forth, right? The code within all three of these functions are just making use of this temporary storage. There's a basically agreement that everything that's allocated from this temporary storage will be cleaned up at the end of this while loop. So at the end of this while loop, basically all of these go away. All of them are freed at the same time, essentially, to be made available for the next iteration of the while loop. So the next iteration of the while loop is starting all over at the beginning of this section of memory. It's like nothing ever happened. So this code is like, oh, this is free now, use it. This is free now, use it. So what that means is there's actually no need at all to keep track of who owns what, because this is just a contiguous address space. You just need a pointer to say at the beginning, this is where the next bit of free space is. And if I allocated it, I move the pointer up here. If I allocate this much, I move the next pointer up here, and so forth. So you only have to remember this one pointer. And then when you reach this point, all you do is put this pointer back here, reset it back to the beginning. And then you're done. There's no keeping track of all the individual pointers. You don't need to remember all these individual pointers and whether they're available, and you need to skip over them to allocate new space or anything like that. None of that matters. So you skip and you don't have to do reference counting. That is, you skip over a lot of that complexity, and for like resetting everything is big O of 1, and allocating a bit of space is big O of 1. It's much cheaper.
Yeah, the reason why he can do it though is because he knows this while loop is how everything works in this game programming language or game framework, because like the module is decided by the while loop. But if you want to make it generic, then it's gonna have to do more stuff to keep up with the ones.
If you can't assume anything about how the program is structured, then but you still want the memory management to work perfectly, then you have to use an automatic management system, which can't use this kind of hacks to optimize it. Do you have any other overall like broad questions about this?
Yeah, I guess if we could, because we talk about like the full garbage collection system and the ARC system. I guess we talk about ARC more, but have we covered like how is the full garbage collection system works? It's like an ARC.
I'm saving that for next time because I know that that's gonna take more time to cover. So yeah, let's save that for next time. If you're curious, in the meantime, if you build JavaScript apps and you use Chrome, then you're using the Orinoco garbage collector, which is the one that's shipped with the V8 JavaScript engine. And I actually saw pretty good talk about it. Is it this one? This category of garbage collectors have one major drawback to it, which is that from time to time it needs to come in and do its job. Because its job is so intensive that it can pause your program while it's doing that.
Okay.
As in, the rest of your program has to be on hold now because the garbage collector is doing its job right now. That's a big reason why some people do not like this full garbage collector and prefer to use something like ARC or prefer to just do it themselves, right? However, like the people who are like doing innovation in this space, they're actually trying really hard to minimize this pause, and the VA team is one of the teams that are working on that.